Today we'll be talking about geometric optics. This is in the approximation where light can be treated as a ray as opposed to a wave. Before we get into geometric optics, it is important that we review AC circuits, as that is important for the third homework problem. First, a couple of definitions. If I leads the EMF, the circuit is capacitive. If the EMF leads the current, then the circuit is inductive. If neither, it is resonant. What it means to have one thing lead another means that if we take the sine curves and we draw them to their very beginning, the one that is leading is the one that has the leftmost start. So let's look at a couple of examples. In each of these graphs, the I curve corresponds to the purple graph, whereas the EMF corresponds to the blue. As we see, I has the leftmost start here, and so I leads the EMF. Since I leads the EMF, this describes a capacitive circuit. They both start at the same time here, so it is resonant. Here, V starts first, or the EMF starts first, therefore the EMF leads the current, and therefore the circuit is inductive. There are two important equations to remember. We reviewed this in a previous recitation, so you should go back and either watch that video or review your own notes. First is the generalized Ohm's law, in which the maximum EMF is equal to the maximum current times the impedance, and it's the magnitude of the impedance. Recall that the impedance is the complex sum of the real resistance, which is the sum of all the resistors when it's in series, and the reactance, which contains information about inductors and capacitors. Tangent of theta, where theta is the phase shift, is given by x over r, where x is the reactance. Theta can be thought of physically as the phase shift. It is the angular difference between the current curve and the EMF curve, so the amount at which one leads the other is given by theta. You can figure it out from the graph. There are other relations that might be important to know. For this problem, it actually might be easier, instead of using tangent, to use another function of theta. We can derive these relations by noting that in the complex plane, it draws out a triangle, where on the real axis you have the resistance, and on the complex imaginary axis, you have the reactance, and their magnitude is z. Therefore, all of these relations hold. Now let's talk about lenses. By definition, lenses are objects which reflect or refract light. Since light are rays, then you can simply draw them on a diagram. They obey the so-called lens equation. The quantities here are important. S is the initial distance between the lens and the object. S prime is the distance from the lens to the image. F is the focus of the lens. First, let's start with the focus. The focus describes the lens in its entirety. Usually it is a given quantity. But if it is not given, then you might have a sphere, in which case the focus is the radius of curvature divided by 2, or you can figure it out from the individual curves that make up the lens, which is given by this formula, where n is the index of refraction, r1 is the curvature radius for the first curve to make up the lens, and r2 is the curve for the second one. You may remember this equation in terms of the signs by noting that for a lens that is an oval shape must have a positive focus. Therefore, R1 must be positive and R2 must be negative. So you know that the signs are very important for this. It is also important to figure out the signs of S and S prime. The way in which you figure that out is by noting that positive distances are always on the same side as light rays, whereas negative distances are on the opposite side of light rays. As such, when you have an object on the left, a lens in the middle, and then the image on the right, you will notice that S will be positive since the light ray is traveling with it. Then, S prime is on the other side, corresponding to the light ray going through the lens, and so that is also positive since it is on the same side. If it so happens that the image appears to the left of the lens, the light ray still goes right through it. But this is now on the left, which is on the opposite side, so in this case S prime would be negative. Now let's consider the case in which you have multiple lenses. We will be discussing an example of this shortly, but the general gist is this. When you have two lenses or more, your image distance from the first lens becomes the new starting distance. Essentially, you will solve the lens equation for one lens while ignoring the second, and then ignore the first lens and solve the second using the previous answer as your starting point for the second lens. Let's look at this following example. The left lens has a focal length of 6 centimeters. We want to find the image, and in fact there will be two images for this example. The object is in between these two lenses. It is 3 centimeters away from this leftmost lens and 9 centimeters away from this spherical lens. The focus of this spherical lens is going to be 3 centimeters since 6 divided by 2 is 3 and 6 is the radius of curvature. The steps in which we will go about solving this problem is to find the direction the light ray goes when it is going to the right, where it will reflect for one lens, and I'm going to ignore the other. Second, I want to find the initial distance, which is given by the diagram, find the focal length, which is r divided by 2 for the sphere, use the lens equation and plug stuff in and figure out what s prime is, and then use that image distance as a new position for the other lens which I did not yet consider. In this instance, there will be two images, and therefore I will have to do the same process twice. The reason there are two images is because the light rays go in two different directions. The light rays can go to the right and reflect off of the sphere, or they could go to the left and go right through the lens. Note that the direction of the light rays is very important. If it is going to a lens, it will go right through it. If it is going to a sphere, it's going to reflect off of it. This will be important for sign analysis, as you will see shortly. Now let's look at the solution. Let's take the light rays which are going to the right through the sphere. We have the focus, which is 3 as we discussed earlier. Then 9 centimeters is the distance to that sphere, and s prime. S prime is going to be 9 over 2. Since it is positive, it will be left of the sphere, since the light ray will also reflect left of the sphere. Since s prime is positive, it must be on the same side as the light ray that is reflecting off of it. Now, 9 over 2 is going to be my initial distance for the lens that is to the left of the object. I'm going to use 12 minus 9 over 2 equals 15 over 2 centimeters. For my initial distance for the second lens, that's our new s. The focus, though, is 6. So the lens equation tells us that once I plug everything in, s prime is equal to 30. Therefore, since s prime is positive, it should appear left of the lens, since the light ray will go through that lens and to the left. And since s prime is positive, it needs to be on the same side as the light ray. Therefore, the first image is a real image which appears all the way to the left of the left lens. Light rays can also go to the left initially as opposed to the right. In this instance, we only go through the left lens since it will not reflect off of it and head back towards the sphere. The image, however, will be negative. Since the light ray goes right through the lens, that means that the image will be virtual and appear to the right of the lens. As you can see, 6 is still the focus, 3 is the initial distance, and s prime will be negative 6. The next important thing to know is magnification. The magnification is defined as the ratio of the final height to the initial height. It can be shown, as you saw in your textbook and in class, that this is equal to minus s prime over s. Either equation can be used. For the multiple lens system, you have to do this twice. We have to look at the first step and then the second step. In the first step, our final distance was 9 over 2 centimeters. We divide this by 9, which was our initial S1. For the second one, we have 30 times 2 divided by 15, because 30 was the final distance, 15 over 2 was the initial distance, and the minus signs cancel, and we get a total magnification of 2. When we involve refraction, the lens equation becomes slightly more generalized. We were looking at lenses in the case where we were just in air, and so the index of refraction of air was constant in 1. In the case where refraction is involved, we have to include indices of refraction as follows. You can simply remember this equation by attaching n1 and n2 over s and s prime, and then the difference will be included there, so more of an average, in which case r is actually the radius of curvature and not a focus. That is important to remember. This is usually involved in equations where you want to solve for the position of amber, which you will see in your homework. Here's an example from the textbook. A Jurassic mosquito is discovered embedded in a chunk of amber, which has an index of refraction of 1.6. One surface of the amber is spherically convex, with the radius of curvature 3 millimeters. I will be plugging in minus 3 into the equation because of the shape. The mosquito's head happens to be on the central axis of the surface, and when viewed along the axis, appears to be buried 5 millimeters into the amber. How deep is it really? This is telling us that the image appears to be 5 millimeters into the amber. Therefore, since the light rays are coming out of the amber and this is inside of it, we have to plug in -5 into here. Then, the initial one is going to be associated with the amber, which has an index of refraction 1.6, and we want to solve for S. N2 will just be 1 since it's air. So, when we plug all these numbers in, we can do the math and find that S is equal to 4. I ask that you do the math yourself. The lateral magnification is minus S prime over S, so M is equal to 5 over 4. In your homework, you have 3 problems. The first is an amber problem. This is similar to our final example, except you want to find S prime and M. The second one is a multiple lens problem. Find the first image, use it to find the second image, and then find the magnification. In the problem, they ask about the real focus. All this means is that you should use the steps, except that the first S is going to be infinitely far away. Note that 1 over infinity has a limit of 0. So this will simplify your lens equation. In number 3, it's a circuit. You're asked to find whether it is capacitive or inductive. You should use the definitions and go over what we did on the first slide. The second part to the problem discusses how to find the resistance. You want to be able to set up 2 systems of equations and try and see which equations help you find R. You don't want to use equations like the reactants which don't involve R. You want to use equations that involve R explicitly. And then another variable that you can relate possibly to another equation. Remember, you only have 2 equations. You have one equation for the phase shift, so you should use one of the 4 given, and then Ohm's law. So think about it that way. I hope you enjoyed it, and I will talk to you and see you next week.